Hello, Chemistry 1110 students. In Chapter 4, we're going to look at some of the periodic trends for elements in the periodic table. One of the first things we're going to talk about, though, is the development of that periodic table. Things, as you know, chemists had been studying the properties of materials for a long time, and they really wanted to organize what had been learned. So in 1864, this gentleman by the name of John Newlands noted that elements arranged in atomic number, every eighth element had similar properties. So in other words, neon was similar to argon. And he referred to this as the law of octaves. And so this is where the idea of 8 being important. Well, 5 years later, Dmitri Mendeleev and another gentleman by the name of Meyer independently proposed the idea of periodicity, sort of building on that law of octaves. And so Mendeleev grouped the elements according to their properties, with the idea that these properties repeat periodically. And based on this, he was actually able to predict the existence of an element, it was gallium, that that wasn't known before his time. However, there were some inconsistencies that Mendeleev could not explain with his periodic table. And an example is that argon comes before potassium in the periodic table, even though it has a higher atomic mass. Now remember, that's based on the protons plus the neutrons. And so, in 1913, Moseley discovered there was a correlation between the atomic number and the frequency of the X-rays produced. And so he said, well, let's order the periodic table by atomic number. And that enabled people to explain a lot of discrepancies that have been seen. And the entries that we see currently in the periodic table are the atomic number, which is critical because that's how they're ordered. But we usually put the symbol, sometimes the atomic, the average atomic mass, etc. And these elements are ordered according to their electron configuration. So here is a question. What elements would you expect to exhibit properties most similar to chlorine? And so you would think in terms of what are the elements that are in the same group as chlorine. And so, of course, you get fluorine, bromine, and iodine because they are all in the same group, that 7A, with chlorine. Now, there's an interesting point here at the bottom that astatine, which is also in group A towards the bottom, is classified as a metalloid. And, you can't compare a nonmetal to a metalloid or to a metal. The properties are going to be very different. And so this is a place where there were discrepancies that have been seen before. And now that we've identified metalloids, we understand why it is not similar to the other 7A members. All right. So here's our modern periodic table, and in this particular version, we have the symbol, the atomic number, and the electron configuration. It's not the one we typically use, but it's one of the ones that's out there. So we're just going to look very quickly at the classifications of these elements in the periodic table. We have what we call the main group elements or the representative elements, and these are sort of the first ones that were discovered, and they have very predictable properties. And so you've got your group 1A, 2A, 3, 4, 5, 6, 7A. Okay. You'll notice group 8A was not included. These are the noble gases. They have a completely filled P subshell. I see my L's were cut off by my picture. And because of these, because they have filled P shells, they are very non-reactive, and we'll be able to understand that a bit more as we move on, I believe. Okay, so once we understood electronic configuration, we could see why there are transition metals, and they're that group formed by filling the D subshells, and they fall down there in the middle of the 3B, 4B, 5B, etc. You'll notice 1B lags because that is where copper, silver, gold have some unusual electron configurations. Check that out from the last chapter if you don't remember. And as they say, group 2B has filled D shells, and therefore they are not technically transition metals because we're not filling the D, it's already filled. However, in common vernacular, they would be called transition metals as well. They are definitely metals. And then the lanthanide and actinides, which you can see drop down even further, are the F block transition metals. Sometimes they're called the inner transition metals. Most of them are radioactive. And once again, they are formed by filling those F subshells. There are, if you remember, 3 P's, 5 D's, 7 F's, and so if you count across, there are 14 elements that make up those F block transition elements. All right, so there is a distinctive pattern in the electron configurations of the elements in any particular group, and I've just listed 2 here. The group 1A, which are the alkali metals. They are like a noble gas with 1 extra electron, which is in the next principal quantum number group. So lithium is like helium with a 2s electron. Sodium is like neon with a 3s electron, etc. In that group 2A, these are the alkaline earth metals. And the difference between the group 1A and the group 2A is just that 2A has that second electron in the s orbital, so it's a filled orbital, giving them very different reactivities. Okay, and so we're going to start talking about those outer electrons, and they are called the valence electrons. So valence electrons are the ones that are involved in forming chemical bonds and therefore chemical reactions. A similarity of valence electron configuration helps to predict the chemical properties. And so for group 1A, as we just mentioned, you have the noble gas with an S1 electron. That's going to be your valence electron. In group 2A, it's an S2 with that over that noble gas core, and so it has 2 valence electrons. And if you go all the way to 7A to the halogens, here you have an NS2 and an NP5, so you have 7 valence electrons. They're all in that outer not filled principal quantum number. All right, so here's a question that you're supposed to answer without using the periodic table. Give the ground state electron configuration and block designations, so whether it's alkaline earth or alkaline metal, that's the S. The other representatives are the P's, the D are the transition metals, and the F are the inner transition metals. For something that has 17 electrons, another element that's 37, and one that has 22, and then you're supposed to classify them. Well, the way they want you to do this problem is to use this little memory aid that you were taught in the last chapter to remember how these energy levels go. So you see that all the S's, there's just one box, meaning one orbital. It holds 2 electrons. The P's are also 1 box, but they hold 6. The D's hold 10. The F's hold 14. And so when we look at that and we count up 17, so we have 2, 4, 10, 12, and then 17 would be 5 in the 3 P's. And so on. So I'll let you take a look at that.